let's get started. As the title suggests, we'll be talking about transistors and circuits. And you might have noticed that we haven't mentioned any specific types of transistors, right? That means it will include both bipolar junction transistor or BJT, as well as field effect transistor or MOSFET. And that's the intention. Although we will focus mostly on MOSFET-based basic circuits here, simply because that is the more cutting edge device. Okay, so let's get started. Here is a symbol of a MOSFET, a typical N-type MOSFET that you see. And the major applications for MOSFET can be divided into two categories: digital applications and analog applications. So when it comes to digital applications, we use MOSFETs to design processors and lots of other digital logic gates. And for these particular applications, MOSFETs act like switches. They essentially act like switches. That's it. You use the gate to selectively turn on or turn off the MOSFET. That's it. And you can allow flow of current, or you can restrict flow of current from drain to source. That's the only feature that we want from a MOSFET to make it operate like a switch for digital applications. But for analog application, it's a different story. It's more demanding, and it requires more complicated design approaches for analog design, by the way. So in analog circuits, we mostly care about time varying signals, and oftentimes we call it small signals, and there is a reason for that. I'll clarify that in a few minutes. And our target would be to amplify that small input signal into something larger when we use this MOSFET as an amplifier. So the most useful or interesting application for MOSFETs in analog domain would be to design amplifiers. And in this particular lecture, we will just focus on the amplifier design. Digital IC design kind of was covered to some extent. Obviously, I wouldn't say it was covered. It was just hinted at to some extent in the previous lecture, which was the last lecture on MOSFET. And if you want to learn more about digital design, you can always take any VLSI course like 433 Introduction to VLSI that I'll be teaching this spring, spring 2021, or any other VLSI courses, or maybe some digital design courses that will help you learn more about the digital applications. And for analog, we have dedicated courses as well. Now, moving forward, let's look at a small signal equivalent circuit of a MOSFET. So you might have, we have talked about a number of equivalent circuits, and I told you already what these equivalent circuits mean. For example, we looked at an equivalent circuit for a diode, a BJT, right? I also gave you some examples of some of the equivalent circuits that I worked on as a researcher. So the target is to represent the different characteristics, different aspects of the properties of a device using the basic circuit components like capacitors, inductors, resistors, stuff like that, right? We somehow mimic the behavior, the high level behavior of a device, of a novel device, which is usually very complicated. And we try to mimic that overall property using this basic circuit component. So that the reason is so that we can simulate that using basic circuit simulators. That's the ultimate goal. And to do that, we will have to break down the overall structure of a MOSFET into smaller components and try to represent different aspects of it with different capacitors or resistors or other circuit components. And on the left, you see a structure, a typical structure of a MOSFET. This is an N-channel MOSFET. That's why you have source and drains as N-type, and the substrate is P-type, right? Let me kind of guide you through this busy figure that we see here. Firstly, see, source and drains are materials, and no materials, I mean, apart from superconductors, will have a resistance-free operation, right? Every material in the world will have some degree of resistances. And because of that, we represent the resistance of the source and drain regions with RS and RD. So these are the simplistic portion. So we have two resistors which we'll be using to represent the practical nature of the source and drain. Even though We just consider that, hey, electrons will come from the source and they will just go to the drain and done. We will get these electrons out. But we don't talk about the non-ideality that this source and drain portions of the device will have. They will have their own resistance. And that's what we are representing using RS and RD. Again, in practice, source and drain, so we might have drawn the MOSFET structure like this, say source, drain, and gate. Source, drain, and gate. And you might have had an idea that, hey, we will just create a channel underneath the gate, which will allow flow of electron from source to drain, right? But that's not really feasible practically. We cannot perfectly align this gate at the edge of the source or at the edge of the drain. We always have some degree of overlap, which you can see here in this figure. See, there will be some overlap between between the source and the gate, and between the drain and the gate. There will always be some overlap, okay? Simply because of the way we fabricate these devices. And because of that, we will have some parasitic capacitances between this gate and source contact, which is represented using CGS. GS stands for gate to source and P for parasitic. So parasitic capacitance between the gate and source. And again, parasitic capacitance between the gate and drain. So CGT, parasitic. Okay, so these are the two components which we will use to represent the overlapped nature of the device. And then there will be some fringing field driven interaction between the gate and the source, some fringing electric field. And those are represented using CGS and CGD. These are not parasitic. These are not result of an physical overlap. This is a result of interaction between the gate and drain using fringing electric fields. By the way, if you take advanced device courses, you will be able to go deeper into these components and see how they behave with different biasing scenarios. But for now, we will just look at a high level picture. Okay, so these are non-ideal capacitances that we're dealing with here. And if you just consider the gate to source portion of it, the total gate to source capacitance will be the sum of these two, CGS and CGSP. And again, the overall gate to drain capacitance will be the CGD and CGDP. And oftentimes the total capacitance is represented as, say, CDS, CGD, gate to drain, and this is CGS, gate to source. Okay, so overall, the total capacitance. And just to make it different from CGS and CGD, we use a T with it to represent total, CGST and CGDT. Okay, total. By the way, while we are talking about these components, let's start making an equivalent circuit for this MOSFET structure. So you see this RD and RS. By the way, this is gate, this is source, and this is drain. These are the three contacts that we're dealing with here, right? We're not showing the body contact or substrate contact here for simplicity. And you see, we have added the drain resistance and source resistance. And also, this is the CGS total, and this is CGD total. CGD is between gate and the drain, and CGS is between gate and the source. Okay, gate and the source. That's where the CGS is. Okay, so let me clear it up a little bit. The point is, we have represented all of these capacitance components, CGS components using CGST, and these CGD components with this CGDT. And then we have represented the resistances of the source and drain using these two resistors, RS and RD. And so that mostly covers all of these components. One thing that's left would be, see, there is this tiny capacitance that's between the drain and the substrate. There is a tiny capacitance between drain and substrate, and that has some interesting implication. Again, like I said, we are not really going into that much detail here, and that's what you see here. This capacitance is between the drain and the substrate. So this CDS is between drain and the substrate. Okay, and one more thing. Remember, this is a field effect transistor. So FET, field effect transistor, it will start conducting current. So current will flow from drain to source when you apply a voltage or an electric field at the gate. right? So it's as if we have a voltage controlled current source through the channel, right? So we can represent the channel as a voltage control current source, and the voltage controller would be this VGS, gate to source voltage, and this GM is something that we will talk about. It's more like the degree of proportionality, that hey, if you apply VGS, how much current will flow through the channel. Say we have a constant, it's more like the current that will flow through the channel, ID, will be proportional to VGS, something like that. And then we could just replace that proportionality with a constant GM, and that GM is called transconductance. So for now, just take it as a parameter, as a constant, and we will talk about how to obtain this parameter in the next slide or so. So this GM VGS represents the overall characteristics of the channel as a dependent current source. And by the way, just to clarify something, we apply VGS between the external gate and source terminal, but we don't get the full VGS appearing across the internal surface. There will be some voltage drop. So let me explain that. So when you apply some voltage at the external gate, which is a metal, there will be an oxide obviously in between the semiconductor and the metal, and that oxide will take a part of the voltage. So there will be some voltage loss, and there will be some voltage loss in terms of obtaining the flat band, more like accounting for the metal semiconductor work function difference. So in summary, you will not get, if you apply 1 volt to the external gate contact, you will not really get 1 volt appearing at the channel. You'll get maybe say 0.8 volt or something. Some reduced amount of voltage will appear at the surface, semiconductor surface. And this VGS dash is the effective voltage that we see between the internal gate. Internal gate will be this thing. This is the internal gate, which actually determines the characteristics of the channel, not the external gate. The internal surface determines the overall characteristics, right? So this VGS dash represents the effective voltage that we will eventually get at the internal gate after all of these losses. Okay, and that's what you see here, VGS dash. Okay, so it appears that we have covered almost everything but one, and that's marked with this red rectangle, and that is RDS, which is not shown in this figure, in this MOS structure. And we will talk about what RDS is in a little bit more detail. Just keep in mind that we haven't talked about that here, right? We will talk about it soon. But just so you know, the channel that we are talking about between the drain and source, yes, drain has a resistance, source has a resistance. So we represent those resistances separately. But the region between the drain and source, that also will have a resistance, right? It's more like a resistance between the drain and source, or channel resistance. And we represent that with RDS. And that RDS can be obtained just by looking at the current voltage characteristics of the overall transistor. And we will talk about that. And oftentimes in some textbooks, you will see it's represented as RO, or output resistance. And there is a reason for that. We'll talk about it, like I said. Okay, so I hope that to some extent explains the small signal equivalent circuit of a MOSFET. And in many scenarios, we keep ignoring a number of these components. Maybe you can ignore the RD and RS components because these are tiny resistances, and you can also maybe sometimes ignore the capacitances between different gate and source, or gate and drain, depending on how you design the device and how accurate you want your calculation to be. But this is the full picture. Now, moving forward, let's take a second look at the overall characteristics of a MOSFET, and let's use a different perspective this time. So this is a MOSFET, right? This is the symbol of a MOSFET, and we have gate, drain, and source. And what we're going to do here is we will be providing an input voltage to the gate of the MOSFET, and this input voltage will be the sum of a DC component and a time varying AC component. So small AC component. It's more like, with respect to time, the input voltage will be like this. It will have a DC component. So it will not start at 0, by the way, right? It will have a DC component. On top of the DC, you will have an alternating component. So this V in will represent the DC level, and this alternating voltage will be the V in, or small signal voltage. Now, when you have a DC component and a time varying component in the input, your current will also respond in a similar way. For the DC component, you will have a DC component for the current, which will not change at all. And then for the time varying component of the input, you'll have a time varying component at the of the drain current. All right. It's more like when you apply a voltage to the gate and you apply a volt. Just to remind you, a transistor only conducts current when you apply VDS and VGS both. That's why the drain current of a transistor is a function of VGS and VDS. You cannot just apply VGS and not apply any VDS and expect some current through the transistor, right? We have to have both of these, VGS and VDS. So we are assuming that we have applied a constant VDS here, VDD, constant VDS. What is the VDS? This is drain and this is source. So VDS will be VDD. VDS will be nothing but VDD because source is grounded here. Okay, so the drain current will be function of VGS and VDS. Now my point is, yes, now when you're varying the gate voltage, that means you're varying the VGS, gate to source voltage, there will be some variation in the drain current as well, because that depends on VGS. And the drain current will have a DC component as well as an AC component. Now, as a result of that, notice that we have a resistor connected to the drain end of the transistor, right? VDD and drain end of the transistor. Say, and that resistor, when this drain current flows through that resistor, there will be some voltage drop across that resistor, right? And that voltage drop, again, simply because the current has two components, a DC component and an AC component. When the current flows through this resistor, the voltage drop will be nothing but current times resistance, right? And when the current has two components, this voltage created because of the current will also have two components. So the output voltage that you see here will have a DC component and an AC component. Okay, I mean, the slide has become very messy. Let me clear it off again. So the point is, because the input has a DC component and an AC component, we will have a DC and an AC component in the current, in the drain current. And because of that, we'll have a DC and AC component in the output voltage. Okay, now, where are we getting at? The point is, see, whenever we have these DC components added with the AC components, for all practical purposes, to make our life simpler, to make our analysis simpler, we can ignore, or we can just ground these DC inputs, right? We can just ignore the DC because those DCs will not lead to any changes in the overall output. The changes in the output will be a result of the change in the input. Only V in will be responsible to the changes in the output, right? So we will get to a reduced version of this circuit in the next slide, next to next slide here, where we will talk about a small signal AC analysis, and we will use the same circuit, but we will simplify the circuit a little bit. But just keep in mind that when we look at the full picture, that means we have DC and AC components. Then if we have a DC and AC component in the input, we will have DC and AC component everywhere in the current and in the output voltage. Now, let's set that aside for a second. So we have just talked about how drain current is a function of VGS and VDS. There is a way to represent that. We could say that the VGS that we apply, gate to source, right? This is gate, this is source. So the VGS will control the drain current. That's what we can say for a given VDS. Just a quick side note here, a little bit tangent. Even though the drain terminal of the drain terminal of the transistor should actually be this. So even though we have applied a VDD in this end, doesn't mean the overall VDS of the transistor, the effective VDS of the transistor will be VDD, because there will be some voltage drop across this resistor, and then the rest of the voltage will go and act like a effective VDS. Just to keep in mind, if we if we didn't have any resistor connected here and we just added a VDD directly, then VDS will be VDD. Okay, just a side note. Now, okay, getting back to the point. we could say that the drain current, the change in drain current, by the way, we are only talking about the AC component here because that's what changes. The change in drain component will be dependent on, or in some sense, say, roughly proportional to the change in gate to source voltage. Change in gate to source voltage is nothing but this AC component, right? And then we could just replace this proportionality with a constant like GM. Let's just, for the sake of simplicity, let's just consider this to be a constant, right? GM. And you can write GM to be ID over VGS. And that's what you see here. GM could be ID over VGS. But this is too much of a simplification. We're assuming that drain current is, always going to be a linear function of VGS, which may not be true. And that is not true, actually. Okay, it's not really a linear function of this. This is a linear equation. That means drain current is a linear function of VGS, but that's not really true. That's what I'm saying, right? GM is not always a constant. So the best way to represent that would be to kind of use a derivative of current and derivative of voltage. So del ID over del VGS. And by the way, when you use del ID over del VGS, that works for linear relationship as well. And it also applies for nonlinear relationships. So it's always a good idea to use derivative. And that's what you do for Ohm law as well, right? V equals IR, as you know, we often use that. Or 1 over R equals I over V. 1 over R is nothing but conductance. And we could just write it as maybe say sigma. We could just represent that sigma I over V. But we don't really write I over V, right? We write di over dV, derivative. And di over dV will be the same as I over V if we have a linear relationship. So it's always a good idea to represent these relationships with derivatives. And that's what you see here finally. GM is not actually ID over VGS. It should be del ID over del VGS. And you might have seen a change here, right? We have suddenly shifted from lowercase ID to uppercase ID. Why? So this uppercase ID, it represents the DC component plus the AC component. But when you take the derivative, the DC is constant. When you take the derivative of a constant, it will be 0. So we don't care. So for all practical purposes, you could just write del ID over del VGS or del the total ID, right? Total ID del total VGS. Doesn't matter because the constants will anyways be taken off. Now, just to simplify this thing, this is the final expression that we should worry about. Even if you don't want to talk about, don't want to remember any of this discussion, just remember this final product that GM, which we use the name transconductance to represent GM. GM is the derivative of the drain current with respect to VGS. And the reason why you have this notation here is because we have a constant VDS. So we are looking at the derivative of drain current with respect to VGS for a given value of VDS, right? That's something that we have to keep in mind. This transconductance is a very important parameter for the transistor characteristics. And we will talk about why that is the case in the next slide, okay? So just remember that. By the way, how can we obtain transconductance GM? Remember, we talked about ID VGS characteristics in the MOSFET lecture. ID VGS, say you have this ID VGS characteristics, right? Now, if I have a Y versus X graph, which looks like this, I can easily take dy over dx, right? That's the derivative. That is the same thing as taking the gradient at each point. And you're just gonna do the exact same thing here. You're gonna take the derivative of did over dvgs. And that's gonna give you GM for a constant VDS. Okay, now moving forward. Here is how we can actually measure. This is another idea to how to measure these characteristics. So now we will not be using ID VGS. We will be using ID VDS characteristics. Now, if you have ID VGS, you can just take the derivative, done. Or you can also use this ID VDS characteristics. And let's look at one of these graphs. Let me change the pen color to make difference. So this is VGS1. So this this particular curve is for a given VGS, which is VGS1. And now let's increase the VGS slightly by a small amount, delta V. And for that slight increase in VGS, you will have a slight increase in the current as well. And that's why your characteristics will look like this. Just so you remember, ID versus VDS is called output characteristics. Remember, an ID versus VGS, we talked about that before, is called transfer characteristics. Okay. Now, so this is output characteristics. We are looking at two curves corresponding to slightly different VGS values. So this is for VGS1 and this is for slightly higher VGS, higher by an amount of delta V. Now, you can always measure for a given value of VDS. See, for a given value of VDS, this is a given value of VDS. For that value of VDS, you can measure this current, which is say I1, and you can measure the next current, which is say I2, and you can always take the difference, which will be nothing but say delta I, difference between this I2 and I1, right? And then you could just divide this delta, let me just write it here. You could divide this delta I by delta V, amount of change in current that you get by amount of change in voltage that you have, and you get the value of GM or transconductance for that VDS. And this particular graph allows you to look at GM for different VDS values. Now, take another VDS, maybe here. Let me change the pen color again. Say, let's take a VDS here, maybe say, this is the VDS. This is the VDS. And then draw a vertical line. You know the amount of delta V that you have, right? You know how much change in VGS you have caused. And then you can always look at this current, say I1, and the next current, I2, and you can always obtain the difference between these two currents, delta I, and you can divide this delta I with delta V to get transconductance for that VDS. So this VDS1, say, right? So you can always, we always have to calculate GM or transconductance for one particular value of VDS. So if somebody asks you that, hey, what is the transconductance for your transistor? You'll have to ask them back that, hey, which VDS do you want to look at the GM, right? For, so do you want GM at VDS equals 1 volt or VDS equals 0.1 volt, or I mean, what do you want? You have to ask them, because GM is only defined at a constant value of VDS. We cannot just generalize that, hey, GM is always 100 or something. Now, moving forward. Now we are ready to look at a small signal circuit for this, for the MOSFET, the same circuit that we have been dealing with. Now, I will not be adding any DC component to it. I will just replace that with only the AC part. And you see, previously we had VDD connected here, but VDD is a DC component. And the DC components are not changing. We will only care about the components that will actually change. So we will replace all of these DC components with an AC ground. So this is not really ground, but for the AC analysis, this is as if it is ground. It's not changing at all. So we will just replace all of these DC voltages to ground. Now the circuit is simpler to analyze. Your drain current component, and notice that we have used lowercase, right? That means we are only dealing with AC component, no DC, will be related to the input through the transconductance. So if you provide an input to the transistor, you know the transconductance, just multiply the input with transconductance, you get the output current. Okay, let me give you another example. Say you have given an input of V PQ, that's your input, and your transconductance is GM1. So how much will be the drain current? The drain current will be nothing but the product of these two things done. That's how much drain current you have. If you know the input, you know the transconductance, you can calculate the drain current. That's how interesting this transconductance is. Now, okay, so our drain current is this IgM over V in. Let's try to find the output voltage. So we have provided an input, a time varying input, which is small signal. Again, that's why small signal analysis. We have provided a small amplitude AC signal, and we want to amplify this, and we will see how the signal gets amplified in this particular simple circuit. We will see that. By the way, we will take the output from this drain terminal. This is the drain terminal. We will take the output from here. Okay. Now, using simple KCL, you can see this drain current will be flowing through this resistor RD. So the voltage that will drop across this resistor will be this drain current ID times the resistor RD. Okay. The only difference here is that with rest, you have negative terminal of the voltage here and positive terminal here. As you know, based on the direction of current, I mean, if the current enters the resistor from this end, this will be positive, and if it exits from the other end, that end will be negative. And because of that, your V out will be negative ID RD. Okay, negative ID RD. Now again, ID could be replaced as GM V in, right? And that's what we have done here. We have replaced ID with GM V in. Now, what we have finally, we have V out somehow related to V in, and amplification is nothing. So amount of amplification could be approximated by looking at the ratio between the output voltage and the input voltage. So we are after that. We are trying to calculate the V out over V in. And if you bring this guy V in to the left hand side, you get something called a gain, a voltage gain, right? How much voltage are we gaining at the output? And the V out over V in ratio turns out to be this thing, GMRD. And now you see that the transconductance of a transistor determines how much voltage gain you can get. By the way, how do you know that you have a gain? If your GM is greater than 1, if your GM transconductance is greater than 1, then you have a gain. If not, then you don't have a gain. So we design the transistors in a way that, by the way, the transistors have a gain. That means the transconductance of a transistor is always greater than 1. So that's why we have a gain. You might wonder that why do we have a negative sign here, and what does that mean? A negative sign in the voltage gain represents the polarity of the output voltage will be the opposite of the input. That means, say if the input is like this, you will have an output which will be exactly, opposite and amplified. That's it. See, it will be just flipped. That's why the negative sign. Okay, so transconductance is an important analog figure of merit. The higher the transconductance of a transistor is, the better the transistor will be as an amplifier. And that's what we use to kind of compare different technology generations. That, hey, this generation of transistor has 20% more transconductance. Then you will immediately understand that they will be better for amplifier design. Okay, and by the way, this is again a measure of the transistor's ability to amplify. Now, there will be an obvious question here. Hey, GM is not the only thing here. There is also another component, which is the RD, the drain resistance. You might say that, hey, by the way, I can just use any arbitrarily large resistor and I can just get any gain out of this transistor that I want, right? You could use maybe thousands of giga ohms of resistance, say, and then you could simply have a huge voltage gain. And we are going to see whether that's even possible or feasible. Right? Just a heads up, it's not. You cannot have any arbitrarily large voltage gain. And turns out this RD will not matter at all eventually. And we will see why. Let's go to the next slide. We will try to find out the maximum gain that we can get from this circuit topology. Before going there, let me again ask you one thing. Just by looking at this expression for the voltage gain, just think about it, whether the gain will be increased if we increase the resistor RD. Yes, right? Because this is proportional. So if we have higher RD, we should expect a higher, in terms of magnitude, obviously, a higher magnitude of the voltage gain. We should expect that. So obviously, the first thing that we should come to our mind is what is the terminal condition? What is the end goal? What if we had an infinite resistance, right? Infinitely large resistance, then we should have an infinite voltage gain, right? Let's see whether that is the case. But before going there, how can we even make an infinite voltage, infinite resistor? And interestingly, a current source, an ideal current source, uh, will have an infinite resistance. Why is that? Let me tell you. So our current source means, say you have a current source of 1 ampere. That means no matter what happens, it will have a flow of current of 1 ampere through it. There will not be any changes to the current because that's the source, 1 ampere current source. The current will be constant all the time. Now, remember Ohm's law, V equals IR. So let me just, again, use some simple algebra here. So 1 over R is V over I. So 1 over R is nothing but conductance, right? Or maybe I could just keep it like this. But remember, this is not the proper way of representing anything. We should use the derivative, dV over di, right? So the resistance will be nothing but di over dV. Now, if the current remains constant, then the derivative of current with respect to, voltage, give me 1 second, let me clear it off again. V equals IR. So 1 over R equals I over V. So 1 over R equals di over dV. I think there was a small mistake in the calculation before, so I just erased everything. I just rewrote everything, right? Just make sure that you don't get confused. So V equals IR is the Ohm's law. When I take resistance to the other side, we get 1 over R equals 1 over V. So 1 over R should be actually represented as di over dV, not I over V, because that's a linear approximation. That's not the proper thing. The proper way would be to use the derivative. Now, if you have a constant current source, that means the derivative of current, rate of change of current, derivative is nothing but rate of change, right? There will not be any change. So this derivative should give us 0 for a constant current source. So 1 over R equals 0. So resistance should be 1 over 0 is infinite. So you should have an infinite resistance. Again, this is hypothetical, obviously, but at least if you can manage to make a constant current source, you have somewhat close to an infinite resistor. And that's what the circuit designers tried to do. I mean, they replaced this resistor. Remember, we previously had a resistor RD. If you go back to the previous slide, here we had a resistor RD. So they tried to replace this resistor with a constant current source. Why? Because that way we will be able to at least approach infinite resistance. And now let's see whether we get infinite gain. Yeah, you could get. We didn't get infinite gain. The reason is we are ignoring another part here. We are considering that transistor is an ideal switch. So whenever it turns on, it will just allow current flow relentlessly. But that's not really the scenario. This transistor will have a resistance of its own between this drain and source through the channel, right? There will be a resistance of its own. And let's see how that resistance plays out here. Let's go to the next slide. We will come back to this slide here in a few minutes, but let's look at this particular figure and show you the resistance that we have between the drain and the source. And we use the notation of R0, output resistance. And there is a reason of calling it RO, which will be apparent when we talk about this slide, which I just skipped. I'll come back to it again. So for the time being, let's just notice that we have a resistance between this V out and ground, and we have an infinite resistance. This current source is nothing but an infinite resistance between V out. And by the way, this VDD can also be considered to be an AC ground because we are doing small signal analysis, right? So let me go back here and let me draw two nodes, V out and say this is ground. Between V out and ground, you have this resistor of R0. So let me draw R0 here, R0. And again, between V out and this is again going to be ground for AC analysis, right? Small signal analysis. So between Vout and ground, you have another infinite resistor, more like this. This is an equivalent representation of that, right? So whenever two resistors are between the same two nodes, say this is A and this is B, we can say that these are in parallel combination. And what is the equivalent resistance of this parallel combination? Just to remind you, say if you have two resistors R1 and R2 in parallel to each other, the equivalent resistance will be, so 1 over RQ equals 1 over R1 plus 1 over R2. And that's what we can get from here as well. Let me erase a few things. Let me erase these things to make it clear. Okay. All right, so now we have an equivalent circuit combination between R0 and infinite. And let's try to get the equivalent resistance here. 1 over R equivalent will be 1 over RO plus 1 over infinite. 1 over infinite is nothing but 0. So essentially you have the equivalent resistance to be R0. So turns out, even when you try to use an infinite resistance at RD, it will not matter. It will be actually limited by RO, or output resistor. So the maximum possible gain that you can get out of a transistor will be what? We will see that here. Will be, instead of, remember we had GMRD before, right? GMRD. We tried to make RD into infinite. But instead of being infinite, it ended up being R0 because of the equivalent resistance scenario. So the maximum amount of gain that we can get out of a transistor will be this GMRO. And interestingly, the maximum gain does not depend on any other external circuit component like resistor. Remember, if we could just control the gain using a resistor, we could have just used any arbitrary resistor and increase the gain as much as we wanted. But we cannot, because this gain is fundamentally limited to two of the fundamental transistor characteristics. Transconductance, that is the property of a transistor. R0 is the output resistance, that is also the property of a transistor. These are all inherent to the transistor. So you just have to make the transistor better to get a better gain. You have no other choice. Okay, that's the bottom line. Okay, so in summary, the maximum amount of gain that we can get out of an amplifier made of MOSFETs will be GM-RO. RO is the output resistance, GM is the transconductance, and like transconductance, output resistance is also an important figure of merit for a MOSFET. So you can, if somebody tells you that, hey, in our technology we have 100 ohms of output resistance, and in some other technology they have 500 ohms of output resistance, you will immediately think that the technology with 500 ohm or higher RO will be a better amplifier, because just look at these characteristics. The maximum gain that you can get will be higher. And by the way, this term GMRO is called self gain of the transistor, GMRO. Okay, just so you know. Now we skipped one slide here, which will talk about how to calculate RO, output resistance. How do we calculate RO? Now that we know the implication of RO and how important RO is, let's try to calculate RO from one of the transistor characteristics. And again, let's go back to the output characteristics of the transistor. Quick reminder again, ID versus VDS is called output characteristics. And by the way, why is that? Because VDS is in the output, ID is also in the output, VGS is in the input. Okay, you might wonder, why do we consider ID versus VGS as transfer characteristics? Because ID is in the output and VGS is in the input, so you're literally transferring the input to the output. So transfer characteristics. And when it comes to ID versus VDS, VDS is in the output, ID is also in the output, so you are restricted to the output characteristics. That's why the name. Now, let's go back to that slide again. So ID versus VDS characteristics, which looks like this. Now, how many of you remember when we talked about the saturation mode and linear mode of a transistor? How many of you remember how the output characteristics looked like in those slides? Actually, let me draw that for you. The output characteristics actually looked like this. I mean, we literally used a flat line, a horizontal parallel, a line parallel to a horizontal x-axis, right? To represent that the transistor has saturated. There will be no more change in current, even though you are changing the VDS. Again, that's an impractical, super idealized scenario. Practically, we can never have this, flat characteristics. There will always be some slope. There will be some degree of change in the drain current with changes in VDS. And uh, let me entail, what if we had a flat ID versus VDS characteristics. We had a flat saturation. Then remember, if you have a Y versus X characteristics, which is flat, what is the slope of this graph? dy over dx will be 0, right? Now imagine I versus V characteristics, in an I versus V characteristics. Again, just to remind you, let me clear these things off a little bit. I versus V characteristics, we know V equals IR. So 1 over R equal I over V, or 1 over R equals di over dV. Imagine that, right? So di over dV, if you had a flat line like this, di over dV will be 0. So if di over dV is 0, then 1 over R is 0. That means R is infinite, right? That means if we could have a flat, perfectly flat output characteristics in saturation, then we could have had a resistance which is infinite in this area. That's the extreme scenario, right? But like I said, we don't have that. We have slight degree of slope here, and the slope that we get, uh, just you can just mathematically calculate the slope using these characteristics. That slope will give you a resistance. Just take the slope in the output within the saturation region, and that will give you the output resistance. And you see, we just literally use the same characteristics, ID versus VDS. But remember, we have to calculate that for one particular VGS here. So output resistance, why are we calling it output resistance? Because we are calculating it from the output characteristics, ID versus VDS characteristics. And the inverse of the slope of ID versus VDS characteristics, just the inverse of the slope, is the output resistance. Okay. By the way, we have to keep in mind that this will be at a constant VGS. That's why this notation, constant VGS. Okay. So if you're given this ID versus VDS characteristics, you can take the slope of this graph and take the inverse of that graph, and you get the resistance at the output resistance. Okay. Now, so we have already talked about this slide. Let's move to the next one. Here we will be looking at some measured real transistor characteristics, even though these are not cutting edge. These are from 2005, published in a conference. And IDM is actually the premier device conference in the world. So we have NMOS and PMOS data, and you see NMOS and PMOS data are like mostly symmetric. There will be some mismatches because of some mismatches in the device characteristics. We are not getting to the details of it, but our target here is to kind of estimate from this real transistor data, to estimate the values of transconductance and output resistance, and to eventually find out the maximum possible gain from this technology. Okay, so first let's try to calculate GM. So GM, remember, if you remember properly, will be, let's go back here again to these characteristics. GM was del ID over del VGS. So change of current over change of VGS. So let's find out. So these graphs are ID versus VDS characteristics, as you see, ID versus VDS. So let's take two of these graphs. What do they represent? They represent different VGS values, and that's what you see here. 1 volt is VGS, 0.8 volt is again a VGS, 1.2 volt is another VGS. That's what they mentioned, right? So let's take two VGS values, 1.2 and 1 volt. So what is the difference between VGS? Delta VGS is say 0.2 volt, and then what is the difference between current for these two VGSs at a given VDS, right? Let's take this particular VDS, 1.2 volt, and the current looks like to be 0.5 and 0.7. So what is the difference between the current? Delta ID is 0.2. And that's what you see here. Delta ID over delta VGS at a constant VDS. This is a constant VDS. Will be GM. Delta ID over delta VGS is GM, transconductance. Okay. And then similarly, we can also calculate the output resistance. And let's take just one line here, because that's going to be, again, output resistance is defined at a constant VGS. So we will not be dealing with two VGS values. We will just be dealing with one particular VGS value. And that's what we have chosen here. So 1.2 volt. And you can draw a straight line and somehow approximate this distance and this distance is nothing but 1.2, say 0 to 1.2, right? And that's what you see here, 1.2. And then you can estimate this distance as well, which turns out to be something like that. And then you can take R0. So essentially take the slope of this graph. I mean, just draw a straight line as a tangent to the saturation portion, and then take the slope of this straight line. That's it. That's, by the way, and take the invert of this slope. That will give you the output resistance. Now, once you know output resistance and transconductance, you can always calculate the maximum achievable gain, which will be GMRO. And notice that we have used the absolute value. Otherwise, we would have had a negative sign here to represent that the output will be, exact opposite to the input in terms of polarity. Okay. Now, having talked about all of these things, let's now look at some topologies for MOSFET based amplifier. So you have already noticed that simple, very simple circuit structure can amplify an input, amplify an AC input and provide as an amplified AC output, right? And I didn't tell you that before, but we have inherently used a circuit topology which is called a common source amplifier. Let me go back to this particular figure here, and I will tell you why that is a common source amplifier. So remember, this is gate, and how do you know which one is drain and source? Whichever one is at higher voltage will be drain for NMOS transistor, and the lower voltage will be source for NMOS transistor, right? So you have ground here, and just imagine, what is the input circuit? This is the input circuit. This circuit is the input, right? So source is a part of the input circuit, and source is also part of the output circuit. So source is common between the input and output. So this will be a common source amplifier. In other words, source is grounded, right? So we have connected ground to the source. That means all the other voltages, input and output, are taken with respect to the source. So source is the common terminal here between input and output. So that's why it's the common source amplifier. And let's go back to that particular slide where we have other topologies as well. Let's look at the common source topology now. So this is our transistor that we are dealing with. This is the resistance that we talked about, just being shown in a different way because this is taken from another textbook, right? Not the textbook that we usually follow. But anyways, so we have gate, drain, and source, and you might notice that source is part of the input circuitry. Let me clear it off again. Source is part of the input circuitry, and source is also part of the output circuitry, right? So source is common, and in other words, you have used ground at the source terminal. So source is the reference to everything, right? So that's a common source amplifier. Let's take a look at another example here. It's a common drain. So this is gate, and oh, I think I should have flipped that. I mean, I'll correct this thing, but this will actually be, say, source and drain. No, this is correct. That's okay. We are looking at common drain. That's fine. So gate, drain, and source. And see, we are going to look at the common drain. That's why we have connected ground to the drain terminal. Okay. Remember, ideally, when you have an NMOS, you know which one is the gate. There is no confusion. But depending on where you applied the higher voltage, say if you apply plus 5 volt here and 0 volt here, this will be drain and this will be source. But for the sake of comparison between these two things, we will consider that this gate, drain, and source are fixed, right? Otherwise, we will not be able to distinguish between common source and common drain, because drain and source are interchangeable. Okay, so that's why in any other scenarios, whichever terminal has higher voltage will be considered drain for NMOS, and opposite for PMOS, by the way. But here, for this particular comparison between common source and common drain, we forget that. We just consider that this drain and source are rigid. This terminal will always be drain and this terminal will always be source. Okay, so that we can distinguish between these two characteristics. Now, notice that drain is grounded here now instead of the source, which was grounded before, right? So drain is grounded, and with respect to drain, we calculate all the other input voltage and output voltage. So this is a common drain amplifier topology. Again, coming back to the next one, common gate, which will be simpler. So gate is grounded now, as you see. So gate will be the basis for calculating all the input voltages and the output voltages. So that's why it's a common gate topology. So there are three possible topologies. It doesn't mean that we will use all of these three to make amplifiers. Turns out the common source amplifier is the most widely used amplifier topology. There are specific, very specific applications which might utilize other topologies, but for the most part, we just utilize common source amplifiers. Now, in the circuit textbooks, for example, the next slide will show you, there is a popular textbook that we often use, Microelectronic Circuit Design by Jaeger and Blaylock. And these, by the way, these figures are scanned. This one and the previous slide, these figures are scanned from that textbook. I just added this gate, drain, source part. Apart from that, everything else is from that textbook. Okay, so you might see some changes in notification, notations like RL instead of RD, they are using RL to represent load resistance or something. Doesn't matter. For all practical purposes, they will exactly be the same. The same concept applies. Now, the point is, in those circuit level textbooks, they will go into much more detail of the circuit analysis. They will try to mathematically reduce this voltage gain and other important parameters. And for the sake of this course, the electronic devices, we are not really going that much into the details of, for example, input signal range, output terminal resistance, terminal current gain. I'm not going to talk about the details of these concepts, but just remember, we just talked about two concepts, right? GM, transconductance, and RO, output resistance. These are very important parameters for transistors. But we haven't talked about all the important parameters that are there for a transistor. And turns out when you talk about analog design, those characteristics are very important. Okay, so that the textbook that I've just talked about, this one, Microelectronic Circuit Design, they have deduced mostly all of this, and then they provided a comparison between different topologies. Now, just so you can see, common drain amplifier has a total voltage gain of almost 1. A gain of 1 means it's not an amplifier, right? Your output is essentially the same as input. So, that's not useful when it comes to amplification, right? So there goes your common drain when it comes to amplification, just so that you can see the implications, right? And by the way, you might remember, so far we have talked about, in a common source amplifier, the gain is nothing but GMRD and negative GMRD, right? Negative GMRD, transconductance and RD. And for this textbook, they have replaced RD with RL, drain resistance to load resistance. They just happen to use a different notation. Now, why do we have a complicated scenario like this here? Because this circuit that we have talked about is slightly different than the one we talked about so far. Let me take you back to this particular circuit. See, we didn't have any resistance connected to the source. We directly connected to ground to the source, directly connected ground to the source, right? There are certain topologies where we use a resistance between the ground and the actual source terminal. And this type of topology is called source degenerate topology. Okay, so when you have a resistance connected between the ground and source terminal in a common source amplifier. That's called a source degenerated common source amplifier. So they have talked about source degenerated amplifier. Now imagine if you want to go back from this topology to the regular one, non-degenerate, right? Non-degenerate condition, then just set RS to be 0. Just set RS to be 0, done. And your RL is nothing but RD, just so you remember. Now let's go back to this one. If your RS is 0, this part will also be 0. And you essentially don't have any denominator, just 1. So essentially you have this negative GM over RL. And remember, RL is nothing but RD. So you have the exact same expression. So nothing changed. Don't worry. Now, I would like to kind of point out one key difference here between common gate amplifier and common source amplifier. You see, common gate amplifier has a positive gain. That means it's not going to be inverting the input, but common source amplifier will be inverting the input. That's the major difference. Now choose wisely, right? Whichever one you want. That's not the end of the story. There are other parameters to consider: input terminal resistance, output terminal resistance. Considering all of this, turns out common source amplifier is usually the more versatile and easier to design amplifier, and that's why it's most widely used. Okay, again, I'm not going into that much detail. The only reason why we are talking about this is because I'm just trying to hint at what you are going to learn in the electronic circuits course, like 336, and you will hopefully go through the details of all of this when you take that course 336. Now let's take a moment to now talk about BJTs. You might have noticed that so far we have only talked about MOSFETs because, again, these are the cutting edge devices, and chances are you can spend your life, if you ever go to chip design industry to work as an engineer or scientist, you will probably end up always working on MOSFETs. You might never have to work on BJTs anymore because we have mostly replaced all of the circuits using MOSFET nowadays. We don't really care that much. Oh, don't get me wrong, we still use BJTs for some highly specific applications. There are some specific applications which make use of some specific characteristics that only BJTs can provide us so far. But we have mostly replaced all of the BJT based circuits with MOSFETs. But just for the sake of comparison and argument, let's try to compare the same circuits with BJT. Now, let me draw two things here. This is a MOSFET. We have gate, drain, and source. Let me draw a BJT, a symbol of a BJT. We have base, emitter, and collector, say, right? So essentially, we have 3 terminal. Forget about the 4th terminal in the MOSFET, right? In BJT, we just have 3 terminal anyways, but in MOSFET, we have 4 terminals. But let's forget about the substrate terminal. Then essentially, you can just replace this this MOSFET with a BJT, and then instead of drain, you can just call, say, collector. Gate, you could call base. Source, you can replace with, say, emitter, right? And that's what you see here in this particular circuit. Just compare that with whatever we had here before. It's as if we have just taken this transistor, just replaced it with a 3-terminal BJT. That's it. Nothing else changed. And same concept applies. When you have ground connected to the emitter, this will be common emitter. When you have ground connected to the collector, it will be common collector. Again, when you have ground connected to the base, it will be common base. And similarly, we can do some circuit analysis. BJTs have their own figures of merit. Remember, for MOSFET, we used GM, transconductance, and output resistance RO as figures of merit to represent how much gain we can eventually achieve out of those devices. For BJTs, we can also do something similar. And eventually, this is a comparison that you will find in the textbook, same textbook. And you see how symmetric these things are. Common collector does not amplify. You have a gain of 1. And common base has positive, common emitter has negative gain. And again, this is source degenerated characteristics. You can always replace RE to 0 and you get the same level of gain, but positive and negative, just to represent. One of them will invert, one of them will not. So okay, so with that, that brings us to the end of this particular lecture, this discussion. I hope you'll be able to learn much more about this field if you keep taking advanced courses, especially uh, I mean, I highly encourage you to take some VLSI courses uh, that will help you get the sense of the overall scenario of the semiconductor industry, rather than just dealing with devices. Devices are only the beginning. You eventually have to have billions of these devices merged together in a system and do something with it, right? You have to use those devices collectively for a specific application or a multitude of application. And how do we do it? How do you automatically do it? uh, there are different types of courses which will focus on different aspects of it, but I will highly encourage you to keep taking courses and eventually possibly uh, maybe try to do some research as well, if your schedule allows. And with that, I would like to stop here. Thank you everyone for listening.